Hey everyone, welcome back. This is Luke from Cadus Maths, and today's video will be about dot products. The dot product is used in vectors and is very important in the application of physics. It tells you how much work is done, and when you multiply vectors using the dot product, the answer is actually a scalar. Let's just review a vector geometrically. A vector can be represented by an arrow. The arrowhead represents the direction that it's pointing at, and the length of the arrow is your magnitude. Algebraically, a vector is represented by its components, x, y, z, and the basis vectors, I, j, k. The vector A has a tittle under, which is the wavy line, meaning it's a vector. When we multiply vectors algebraically, we only multiply the components and add them together. Let's take example vector A and B. And we say A dot B. Let's now write out our vectors algebraically and have a dot between them. We're now going to look at the components and multiply them respectively. So 2 times 3, the components of I, 2 times 2, the components of j, and 3 times 2, which are the components of k. And the answer is 16 without any vector symbol, as the dot product equals a scalar. Let's now see the dot product geometrically. We're going to introduce a number plane, and we're going to draw two vectors, a yellow and a pink one, all starting from an origin. Let's call the yellow vector vector A and the pink vector vector B. You notice that there's an angle in between these two vectors as they originate from the same starting point. If we're not given the algebraic representation of a vector, but we know the magnitude or the length of the vectors, we use a different formula. Let's now review the modulus, or the magnitude of a length. We often use the Greek letter lambda to represent magnitude. Remember that magnitude, or the modulus of a number, is its length, and it needs to be non-negative. So to find the modulus, we square root and we add the sum of its squares. The Pythagorean theorem can help us visualize this. We represent the hypotenuse c and its lengths a and b, knowing that c squared is equal to a squared plus b squared. So the longest length of a right-angled triangle is c, which is equal to the square root of its lengths a and b squared. We can use this equation and apply it to the length of vectors. We just replaced c, a, and b with a vector and its components. Let's do an example of vector E with the equation 3i minus 2j plus 2k, and we need to find the modulus of this. We represent the length or modulus of a vector using a bar. Some use 2 bars, but for this video we will use 1 bar on each side. So we square each of the components of the vector, 3, 2, and 2. As we know that the length has to be non-negative, the answer gives us the square root 9 plus 4 plus 4. So the length, or the magnitude of vector E, is equal to the square root of 17. Let's now bring back our vectors from the number plane, A and B. From before, we saw that the angle theta between these two vectors, theta needs to be between 0 and pi. Let's say for this example that theta is equal to pi on 3. Why is cosine used in this equation to find the dot product? Well, remember, vectors need to be pointing in the same direction. If we know cosine theta and multiply it by the magnitudes of vector A and B, you can now multiply vector A and B since they are pointing in the same direction. For this example, let the magnitude A and B be 5 and 6. And let's have a look at our formula, which is A dot B is equal to the lengths of vector A, length of vector B, multiplied by cosine theta. We're going to put in our values, and we're going to use the exact value for cosine pi on 3, which is half, 30 times a half is equal to 15. This gives us a scalar value. I hope you enjoyed the video. Just remember the dot product always equals a scalar. Thanks again for watching, and I'll see you in the next one.